Okay, today's lecture we will be coming close to finishing reactions of amines. So the first thing that I want to talk about is I want to talk about the basicity of heterocyclic amines, which is going to be different and take us back to the idea of aromaticity and heterocyclic aromaticity. So let me start with the idea of this molecule pyridine. Now, pyridine has a basic nitrogen in it. First of all, this is a heterocyclic amine, meaning that the nitrogen is part of an aromatic ring system. So that's what makes it heterocyclic. But this nitrogen in pyridine is basic. And in order for the nitrogen in a heterocycle, particularly an aromatic heterocycle, to be basic, the lone pair must be available to donate to a proton in order to basically protonate that nitrogen and make it basic. So, for instance, this is a pyridinium called a pyridinium ion. So this is a basic nitrogen. So if the nitrogen is part of or is not part of the aromatic system, it's available to bond to H+. But what if it is part of the aromatic system? So let's go to pyrrole that we talked about back when we were talking about, is it aromatic, is it non-aromatic, or is it anti-aromatic? So in the case of pyrrole, remember that pyrrole was aromatic. So first of all, this is pyrrole, and pyrrole was aromatic. And the fact that it is aromatic means that all of the atoms are sp2 hybridized, so it's planar. And the nitrogen chooses to be sp2 hybridized so that it is part of the aromatic system. So if you remember, if we drew this out, what happens is nitrogen becomes sp2 hybridized. It puts its lone pair in the p orbital, and this is a 5-membered ring, so let me just redraw that. 1, 2, 3, 4, 5. So then all of the other carbons have their have the double bonds. So the nitrogen becomes sp2 hybridized, and then that lone pair can become part of the pi system. It already has 4 pi electrons. If it included that one, there would be 2 more, so it would have 6 pi electrons, and therefore would be aromatic. Now, once a nitrogen uses its lone pair, and its only lone pair, to be part of the aromatic system, that lone pair is no longer able to bond an H+. So if we added acid to this, that cannot happen. The lone pair on the nitrogen is part of the aromatic system, it's part of the aromatic pi system, and it is not able to bond an H+. Okay, so when you're looking at heterocyclic amines, whether the nitrogen is basic or not is dependent on whether the lone pair number 1 has lone pairs, and number 2, if those lone pairs are part of the aromatic system to make the system aromatic, then they are not able to bond an H+. Another example of a non-aromatic nitrogen would be something like this. if we had this 5-membered ring, then what would happen is that the nitrogen again could be sp2 or it could be sp3, and it's going to choose to go sp2 if it will make the system aromatic. We have 2, 4, 6, 8. If this becomes part of the pi system, we now have 2 more, so we have a grand total of 10 pi electrons, and that would make the system aromatic. So in this case, the nitrogen lone pair is part of the aromatic pi system and therefore not able to bond H+. So that means that this nitrogen is, the nitrogen is not basic. Okay, so that's just kind of a review and fills in Top Hat when they talked about the basicity of heterocyclic amines. The nitrogen will be basic if it has a lone pair to grab or to donate to an H+ that is not part of the pi system. As soon as the nitrogen uses its lone pair to become part of the pi system, then it is no longer basic. Okay, next let's talk about the nucleophilic aromatic substitution reactions that can occur in a heterocyclic aromatic system. So first of all, when you have a heterocyclic amine, the one thing that we should note about this is that, for instance, for pyridine, which we'll do our reactions on, that this is going to be less reactive than benzene in some reactions like electrophilic aromatic substitution, which I'll get to, but it also may provide for nucleophilic reactions. The reason it's less reactive in EAS is it's less electron rich. So in nucleophilic aromatic substitution, we can do reactions like this. We could say, let's react our benzene with something like NH2-. And if we do that, we can actually do a sort of a nucleophilic substitution reaction. And what will happen is, the question is, of these positions, where will the nucleophile add to? The position next to the benzene ring, the position next to the nitrogen in the aromatic ring is going to be where the reaction occurs. So this N- is going to come in, add to that carbon, and then this pair of electrons would go to the nitrogen. So if I do that, I'm going to get there's an H, then there's my NH2, and then my double bonds there and there. So that nitrogen now takes on the negative charge, which is perfectly fine because nitrogen doesn't mind having a negative charge. So to reform the aromatic ring, we have the pair of electrons goes here, and then H will come off as essentially an H-. It's not a great leaving group. That H- will deprotonate something else. Actually, in the textbook, this is what they say happens. As that H- comes off, it deprotonates one of the nitrogens. We form the double bond. We now have an NH with a negative charge because the H minus has removed the hydrogen there, and then that will basically deprotonate something else. So when we add H2O at the end of this reaction, the NH minus will deprotonate the water to form NH2 and a hydroxide. So this is kind of a direct substitution on something like a pyridine ring. And again, the position where the nucleophile is going to add is next to the nitrogen, or in an ortho position to the nitrogen. Okay, so that's one example of nucleophilic aromatic substitution. The other true nucleophilic aromatic substitution that we can do is to, again, take something like pyridine, and let's say we were to add something like methoxide to that. And let's put a halogen here like bromine. So you can do direct, or you can do a nucleophilic aromatic substitution on this reaction. The mechanism is going to look very similar to what we did before. The minus charge is going to come in. A pair of electrons will go to the nitrogen. So the nitrogen is going to have two lone pairs, which means it gets the negative charge. And then the OCH3 and the Br are now attached. We could draw other resonance structures here, and let's just go ahead and do that. So you could take this pair of electrons, move it here, but then this pair of electrons would go to that carbon. Remember, when you're doing anions, you're moving the pairs of electrons to a carbon. So in this case, the negative charge would go there. Then if I wanted to bring that pair of electrons, the pair of electrons would go to the other carbon on the other side. So I could form that resonance structure, and then this pair of electrons would come down to reform the aromatic ring. Bromine versus OCH3, which one's a better leaving group? The halogen is a much better leaving group. So we would then lose a Br minus and be able to reform the aromatic system. But now what I've done is I've substituted the methoxy group for a bromide. So this is an example of nucleophilic aromatic substitution on a heterocyclic aromatic molecule. Okay, and it's very similar to what we saw for the nucleophilic aromatic substitution without resonance stabilization. I guess I have to say that it looks more like what happened when you had an NO2 group or C triple bond and some sort of deactivating group, or, well, it's an activating group in nucleophilic aromatic substitution, in other words, an electron withdrawing group. So that's nucleophilic aromatic substitution on a heterocycle. Now what about a electrophilic aromatic substitution? Well, if we were going to do that reaction, if I'm going to add an E plus to the benzene ring, then the question is, where should I add the E plus? Should I add it to carbon A, carbon B, or carbon C? All right, well, let's add it to A, to B, and C and see what we get. What do I mean by that? Well, let's add E+. Let's draw out the resonance structures. The point where we have the most resonance structures is going to be the one position where we add the E+. Okay, I could make this a take-home quiz problem. I have another one that I'm going to make a take-home quiz problem, so we won't worry about that right at the moment. All right, so here is my molecule. Let's go ahead and add it. Let's take that pair of electrons. Let's add the E+ to that carbon. That puts the positive charge on the nitrogen. Then this pair of electrons can go there to form the resonance structure. Put the positive charge there. And then take this pair of electrons, move it here to form the third resonance structure. Now, before we evaluate that, let's draw the other ones. Now let's add the E+ to carbon B and draw out the resonance structures. Okay, now let's draw out the resonance structures for adding E to the B position. Okay, so there's resonance structure number 2. Let's go ahead and move this pair of electrons over here. And put the positive charge there. Okay. Let's draw a third. Let's add it to C. Resonance structure number 1. Resonance structure number 2. Resonance structure number 3. Okay, so what we did in the past when we added electrophiles to the different positions was we basically looked at the resulting resonance structures and said, okay, which one of these is the combinations produces the most stable resonance structure for the resonance hybrids. So let's look for any that are particularly good. or any that are particularly bad. And, you know, if you're an overly ambitious go-getter student, stop the video right now and kind of look at these and say, well, are there any resonance structures that are really good or really bad? Really stable or really unstable? Okay, if you did that, I'm not real thrilled about this structure because I put a positive charge on the nitrogen. That same resonance structure is down here. So again, these are probably going to be less stable resonance structures than the other ones. You might be tempted to look at this middle resonance structure right here and say, can I draw a fourth resonance structure for that? Let me try and do that down here and say, yeah, not going to work. So let's say that I took this pair of electrons on the nitrogen and I wanted to donate it to form another double bond. Let's just say I wanted to do that. So I wanted to form something like this, where the positive charge would go on the nitrogen. Okay. So let's say I wanted to try and do that. I hate to mess this up, but what about that resonance structure? Boy, that has so many bad things going for it. Well, it has two bad things going for it. Can you guess what those are? Number one, nitrogen with a positive charge. That's the least of our problems. This nitrogen, in order to have two double bonds, should be sp hybridized. What about sp hybridization? sp hybridization says there should be a 180 degree bond angle. That's 120. So as tempting as it is to draw this resonance structure, it's too unstable. And that's perfectly fine. So of this combination of adding to the ortho, to the meta, and to the para positions relative to the nitrogen on the ring, which combination is the most stable? Well, adding to the meta position, because at least I get three resonance structures that are relatively stable, whereas adding to the ortho position, that one's not particularly stable, and to the para position, that one isn't. So when we add electrophiles to a pyridine, a six-membered ring, it's going to go to the meta position. Okay. Now, we need to have a take-home quiz. Actually, we need to have a take-home quiz. And the take-home quiz, because you need to do this for yourselves, I would like you to do that same analysis, adding to the position A and position B of the pyrrole ring. So I would like you to add E plus to the pyrrole. I would like you to draw all of the resonance structures. And then draw a conclusion to where the E plus adds to A or to B. and then just give me a quick explanation why. Okay, so that's your take-home quiz. There won't be an online quiz. That will be your take-home quiz. Go ahead and write that out, and there'll be a place for you to submit a picture of that, and then I will go ahead and grade it. And that will be, this will be due by 11:59 p.m. April 8th. And I hate to put time, I hate to put dates in here because then I won't be able to use this video again. But it'll be due on by 11:59 on Wednesday, April 8th. Okay. So you can go ahead and do that, and we'll figure out with a 5-membered ring, where should the E+ add. Okay, same analysis you did on the exam recently. Okay, let's talk about a couple of other synthesis of reactions of amines. Number 1, amines with carboxylic acids. If you take a carboxylic acid and you add an amine to it, what's going to be the reaction? Now hold off if you think you're going to add the amine to the carbonyl group, because you are not. This is a carboxylic acid. This is an amine. What is an amine? It's basic. So when you react a carboxylic acid and an amine, you are going to get an acid-base reaction. And what you're going to end up doing is the amine's going to deprotonate the carboxylic acid to make the carboxylate, and the nitrogen in this case will pick up that proton to form an ammonium and become an ammonium. So this is called an ammonium carboxylate salt. Okay. And that's what happens. So just adding an amine to a carboxylic acid will not make an amide. An amide being replacing the OH with the amine. That is an amide. You can still make an amide from an ammonium carboxylate by simply doing the following. Heat. If you heat that, what you'll end up doing is you'll end up losing water, and you'll end up basically forcing the nitrogen to form the amide. But it requires heat. Okay. Back years and years and years ago, my first graduate student, when the chemistry department had master's students, we had to figure out how to take carboxylic acids and add amines to them, and we were using an amine that had a nitrogen 15 enriched atom in it. And so we found this reaction, and we tried it with, for instance, a hot plate or a heating mantle, but it turned out it was like a 1910s paper. It didn't work very well, so we had to go back and think, okay, now how in 1910 would they have heated a round bottom flask after making this ammonium carboxylate? And what we found was that we actually had to use a Bunsen burner and heat the snot out of it in order to convert the ammonium carboxylate to the amide. And so this heat is pretty significant. But that's how you can form the amide. But you won't do it on the first step. You need that second step of heat. Okay, so that's one reaction of amines with carboxylic acids. Now, you can make an amine a lot easier by simply taking our friend, the carboxylic acid chloride, and it will definitely become our friend in the next chapter, or next couple chapters. So if you take an acid chloride and you react it with that same amine, you can make the amide very easily. Okay, very easy to do. I will also say as an aside that if you remember in lab, I'll write the exact molecule we had. Remember that in lab we had a benzene ring with an NH2 group on here. Remember down here we had our methyl group. And we actually made the amide by using the acetic anhydride. We'll talk about this reaction in the next couple of chapters. That's another way to make an amide very nicely. And we did that in lab. So you can do either reaction to make an amide using either an acid chloride or using an anhydride. I want to talk about the acid chloride for the minute because it's going to lead into the next reaction. Now, just as a reminder review, how did we make the acid chloride? We took our carboxylic acid, and what did we add to it? If you said HCl, you're wrong. If you said SOCl2 or PCl3, you're correct. HCl will not work in this reaction. Only SOCl2, only PCl3. So that's how we make the acid chloride. But you can very easily make the amide by reacting the amine with either an acid chloride or acid anhydride. Okay. Now, why would those reactions be important? Well, I'm going to take a little aside here, and I'm going to kind of jump ahead to the end of chapter 23 that we're in, and then we'll go back and talk about Hofmann and Cope eliminations. But I want to talk about sulfa drugs and sulfa amides. So here is a structure of a basic sulfamide, or sulfa drug. Now, what are sulfa drugs? Sulfa drugs are basically what are considered to be sort of the first of chemotherapy drugs. Chemotherapy meaning a chemical to treat cancer or treat a disease. And these sulfa drugs were actually some of the first drugs that were developed to fight infections, and they were used extensively in World War II. Typically, in World War II, a soldier was given a packet of a sulfa drug so that if they were injured to combat infection, or if they got an infection to treat the infection, they had some of this sulfa drug to be able to put in their wound to kind of help protect against infection, or if they had infection, to help this. So this was a first idea of using a chemotherapy or a chemical treatment of a disease. And I actually have one of these in the lab that I bought somewhere online, just as an example. I think it came from Brazil for some reason, but anyway, it's one of the sulfa drugs that a GI or a soldier would have in World War II. Now, this is the structure of a sulfa drug. Basically, what you have is you have an amine on the benzene ring, and then over here you have the sulfa part where you have another amine attached to an SO2 group. And so that's the basic structure. You can vary the different alkyl groups that are attached to the nitrogens, and you can make a variety of different sulfa drugs. Some are more effective than others. So sulfa drugs were so important in World War II that Disney decided that they were going to do a cartoon. This is kind of war propaganda, but to show how important sulfa drugs were to kind of the war effort and how they could be used. And if you want, you can try and find this online. I actually own an original copy of this. It's in one of my offices on the wall. This is a picture of my copy. This is one of those things that if you find it online, they're going to be Disney made a cartoon of what? It was used, sulfa drugs were used to treat things like gonorrhea and syphilis, and there's Mickey down here because he took some against doctor's orders. As a matter of fact, in the slide before that, he's gulping down all these pills. There's a discussion about, well, chemotherapy. Let me get my laser pointer out here. So there's Mickey gulping down a bunch of pills after being told by his doctor that this was strong medicine. Don't do that. He did that. He gets sick. But they're talking about chemotherapy, not in the way we think of chemotherapy today, but in chemotherapy in terms of the drug treatment of a disease. So the Disney animators went kind of nuts on this, but it kind of shows the idea of the importance of that. And then down here, it's like down here in this box right here, there's some commentary on how important it was in the war effort. And this came from a magazine of about 1945, 44, 45, 46 vintage. So that's why it was basically war propaganda. But it kind of is instructional in terms of how people started to look at these sulfa drugs. Okay, so let's get to the chemistry of them. Oh, we'll have to go to another. So how do we make a sulfa drug? The way we make a sulfa drug is we start with our benzene ring and we put our nitrogen on the ring. We know how to do that, right? We could go from benzene to putting an amine group on the ring. First, we know that we could put ammonia on the ring, NH2, and now we know how to alkylate it from this chapter. So we could alkylate the nitrogen with whatever groups we wanted, which is great. But now let's put the other end. So here's my sort of synthetic scheme. What I would do is I would say, okay, I have my nitrogen groups on the ring. Maybe I just put one alkyl group on there. And what I want to do is now I want to put the sulfur group on. So I'm going to put an SO3H group on the ring. Then what I'd like to do is I'd like to put a nitrogen group on that OH. I can't do that in one step. So here's what I'm thinking. I'm thinking that if I change that SOH group or that OH group to a Cl group, then this group right here is going to be the equivalent of a carboxylic acid chloride, so that then I could react that with my next amine group and attach that nitrogen to it, attach that amine group, and make basically whatever my sulfa drug is. Okay. Well, what reagents would I use? SO3, H2SO4 to put the sulfonic acid group. That sulfonic acid group would go para. Why? Steric hindrance, right? Sort of like what we talked about with protection, or sorry, not protection, blocking, a blocking group. Then, how do I convert the SOH group into an SCl group? SOCl2 or PCl3. That's why I talked about the acid chloride group earlier. So this is kind of an example of a way to synthesize a variety of different sulfa drugs, and we could do that very easily knowing all of our steps on paper. And so that's kind of how we would synthesize them. That is how we would make these types of sulfa drugs from basically benzene. We know all the reactions for that and the importance of kind of a historical context in terms of the importance of sulfa drugs. Okay, so let's go back and talk about the last two reactions, and we may only get to one here. Hofmann elimination. Now, where have we seen Hofmann elimination before? If I was going to do an E2 reaction on this alkyl halide, I have choices of bases, right? I can use tertiary butoxide, or I could use NH2-. I could also do this reaction by E1. Looking at this, I have two. Here's my alpha, here's my beta carbons, and there are my two beta hydrogens. Remember, these bases, or E1, is going to produce two different products. I'm either going to form the double bond to the left, or I'm going to form the double bond to the right. Which one of these two is the more stable product? The one on the right. So what did we call that product? We called that the Zaitsev product. What did we call the product that was less stable? Well, we could have called it the Hofmann product, and it may have mentioned that casually. The Hofmann product then is going to be the least stable product. And now it's time to talk about where that term comes from in terms of Hofmann elimination. Now, which reagent gives you what? Well, tertiary butoxide, remember, removes the beta hydrogen that is the least sterically hindered or most accessible, and NH2- can remove both of them, but will prefer to form the more stable product, and of course E1 produces the more stable product. So that's kind of a review of where Hofmann has shown up in the past. So Hofmann elimination means that when we do this reaction, we are going to form the less stable double bond. How are we going to do that? Well, let's start with something simple. Let's start with this amine. And let's exhaustively alkylate it. What do you mean? Here's what I mean. Let's react it with methyl chloride. Remember what happens? SN2 reaction. I form my ammonium chloride salt. I treat that with base, and the base is going to remove one of the hydrogens, So I'm going to form the free amine. Let's treat that with a second equivalent of methyl chloride. We're going to do another SN2 reaction. I'm going to form another ammonium salt. And the chloride is going to be the counterion. I'm going to treat this with hydroxide. The hydroxide is going to come in, remove that hydrogen. So now I formed my tertiary amine. And I'm going to do this one more time. Treat this with methyl chloride. Kicks off the chlorine. And now I make the ammonium. Now, that ammonium turns out to be a pretty good leaving group. In other words, I can take this pair of electrons and give it to the nitrogen, and that whole group will leave. So the ammonium then becomes a good leaving group. Well, so in other words, if all I have to do is then treat this reaction with something like hydroxide and heat, and it will basically eliminate the tertiary amine, I will lose a hydrogen, and I'll form the alkene. So the hydroxide, usually there's just a little bit of hydroxide that's necessary, and I'll show you how people have done this in the past in a moment. Well, what is the major product of this reaction? Well, it turns out that when you do this reaction, what you end up doing is you end up losing the hydrogen from a carbon that has the most hydrogens. So you end up losing an H plus from the C with the most hydrogens. And I'm going to say it that way as opposed to any kind of sterics, because there's no real sterics involved here. That's the carbon with the most hydrogens. And so that's where I'm going to lose my hydrogen, and my ammonium is then going to leave. So I'm going to form the least substituted double bond. All right, now why? Why in this mechanism do I lose the hydrogen from the carbon with the most hydrogens versus the carbon with the less, that has less hydrogens? Well, that's going to have to do with the conformation. So if you think about this molecule, and there are 3 methyl groups here. There are 2 hydrogens over here, and there are 3 hydrogens here. The reason that we're preferentially going to lose the hydrogen from the carbon with the most hydrogens is because that carbon has the most hydrogens that can become anti-periplanar to the ammonium group. Now, this is going to get ugly, but let's do it anyway. Let's draw the Newman projection looking down carbon 1, carbon 2. And let me draw it so that the front carbon looks like this and the back carbon looks like that. So on the front carbon here of carbon 1, there's 3 hydrogens. Here is my ammonium group. And then off of that ammonium, there's a hydrogen, so there'd be a hydrogen, and then there would be the ethyl group. Now, any of these 3 hydrogens can become anti-periplanar to the nitrogen. So I have 3 hydrogens that can become anti-periplanar. And also notice that there's no preference of one over the other. They all would have the same exact conformational energy. Let's reverse this and now look down the carbon 3, carbon 2 bond. And again, I'm going to do the same thing. I'm going to draw the front carbon like this and the back carbon like this. So on the back carbon, I'm still going to have my nitrogen with my 3 methyl groups and the positive charge, but now attached to carbon 2 is a hydrogen and the methyl group. Looking down carbon 3, what do I have? I've got 2 hydrogens and a CH3 group. Now, first of all, there's only 2 hydrogens that can become anti-periplanar. So that reduces the likelihood of losing an H+, but it's more than that. Notice that this methyl group is not in the most stable conformation here. That methyl group would probably the most stable conformation of that would look like this. Right, I mean, putting the methyl group over here, putting the methyl group in this position would put it gouged to a fairly large ammonium group. So this is probably going to be the most, I'll put that in quotes because I don't have any evidence of that, but that's easy enough to calculate, most stable conformation. Well, there's no hydrogens anti-periplanar to the nitrogen. So in the most stable conformation, up here, I have 3 most stable conformations. And all of them have hydrogens. All of them have a hydrogen anti-periplanar to the ammonium, to do E2. But down here, the most stable conformation has no hydrogen anti-periplanar to the nitrogen. So therefore, in Hofmann elimination, this is going to be the major product because it has more hydrogens that can be anti-periplanar to the nitrogen. And number 2, all 3 of those have the same energy, whereas over here, with a more substituted carbon, those alkyl groups are going to cause less hydrogens and a less stable conformation. So this is the reason why you form the double bond. You form the double bond to the carbon with the least number of hydrogens. Okay, leading to the less substituted double bond, the Hofmann product. Not the Zaitsev product, the Hofmann product. Okay. So in Hofmann elimination, that's what we make. In my last minute here, I want to talk about how we would really, how would I say do this reaction? I would start with an amine, and here's what I would say. I would say let's go ahead and use three, well, not in brackets. Let's use 3 equivalents of CH3Cl. What about the base? What most people do is they use this. They use silver oxide and heat. What's the purpose of silver oxide? Silver oxide dissociates in water to form 2 silver plus ions and a hydroxide. Basically the oxide 2 minus reacts with water to form then hydroxide. So if you use silver oxide, what happens is the small amount of hydroxide that is present is going to go ahead and deprotonate whenever you form your ammonium salt. That hydroxide will go in and deprotonate and make the free amine. The free amine will then be able to react with another equivalent of CH3OH. And so what happens is that as that hydroxide reacts, this equilibrium shifts so that you produce more hydroxide. Remember, silver hydroxide is basically, quote unquote, insoluble in water. Although it's really not, right? There's a Ksp value of solubility. And so what happens is if we just use a little bit of silver oxide, it produces hydroxide as we need it. The hydroxide reacts, it produces more, and so that allows us to do this reaction. So these would be the conditions for this reaction, and then the major product of this would be that, and this would be the Hofmann reaction. Okay. All right, so if you have questions about that, we can go over that in the next Zoom lecture or Zoom question and answer period. And what we'll finish up in chapter 23 is the cope elimination, which is similar but different. And we need to talk about, there's one more thing we need to talk about this, but my time is up. We need to talk about the stereochemistry. And the key thing with the stereochemistry is that the anti-periplanar geometry is important. Okay, so we'll pick that up next time, and then we will move to cope, and then we'll move into carboxylic acid, which is chapter 24. Okay, so just as a quick summary, this is the quiz for Wednesday to do this problem. Okay, other than that, I will see you in the next video.